Orbiting is an interesting aspect of gravity. There are many mechanisms that determine how orbits work. I will take you through those mechanisms so you can learn how they work. The first mechanism is orbital velocity. That is, how fast an object needs to move to stay in orbit. Orbiting is just a balance between gravity and centripetal force. To stay in orbit, the force from centripetal force must be equal to the force from gravity. Therefore, we can set the equations for each force equal to each other and solve for velocity. As you can see, orbital velocity is equal to the square root of the gravitational constant times the mass of the object being orbited divided by distance from the center of the object. This means that orbital velocity decreases as distance increases, which makes sense because gravity decreases the further you are from an object. This is what a graph of distance versus orbital velocity looks like. Using orbital velocity, we can also calculate orbital period. To do this, simply divide 2 pi times distance from the center of mass by the orbital velocity. This works because 2 pi times distance is the circumference of the orbit, which means that that is the distance to be traveled in one complete orbit. This gives us a graph of distance versus orbital period. The orbital velocity mentioned before only works for perfectly circular orbits. No perfectly circular orbits actually exist in nature because perfection is impossible. However, it is useful for nearly circular orbits. All orbits are actually ellipses. Circles have one center, but ellipses have two, called foci. When orbiting in an ellipse, the object being orbited is at one focus, and there is nothing at the other. Orbital velocity goes up and down in this kind of orbit. At the farthest point, the apoapsis, the speed is slowest, while at the closest point, the periapsis, it is fastest. This makes sense with the original version of orbital velocity because tighter orbits have faster orbital velocities than larger ones. However, with elliptical orbits, it is even more of a difference than there should be based on the original equation. The reason is that if the object had a normal orbital velocity for its closest point, there would be no reason for it to go back up to its farthest point. It would continue in a circle, never getting farther away. That is why, at closest approach, the object is moving faster than it should be. This gives it that extra kick to distance itself again. At its farthest point, it's just the opposite. The object is moving slower than it should. It can't maintain its distance in the orbit, so it falls back down to its lowest point. The equation for orbital velocity in an elliptical orbit is this. A stands for semi-major axis, the average distance from the orbiting body to the center of mass. This is the graph for the equation. An interesting thing about the way elliptical orbits work is in space travel. When you throw something in the air, its path through the sky is calculated as a parabola, but really that is just an extremely close approximation. The object thrown is actually on an extremely elliptical path that, if it were unimpeded by the ground, would be able to orbit around the Earth. This means that after the first stage of a rocket launch, the rocket is on a slightly less elliptical orbit that will still make it plummet into the ground. To stop this, the rocket can do a fuel burn exactly at the apoapsis in the direction of motion. This increases its speed without increasing its distance from Earth. So, the only factor in the orbital velocity equation that can change is the semi-major axis. And if the average distance increases without the maximum distance changing, the only thing that changes is the minimum distance, the periapsis. Because of this, the rocket is now in a safe orbit. This technique works at any apsis. Force in the direction of motion increases the distance of the other apsis, while force in the opposite direction of motion decreases the distance to the other apsis. These methods work because you are either increasing or decreasing a deficiency or excess in speed. Fuel burns in different directions at different points in an orbit have different effects, but these are very simple ones. All in all, orbiting is a balance of gravity and centripetal force. Using that fact, we can find out how fast an object needs to move to stay in orbit. On top of this, objects that are moving slightly too fast or slow for their orbit are really part of elliptical orbits. These elliptical orbits allow for interesting maneuvers in space travel.